Okay, let's get started. Good afternoon, everyone. I am Pratap Reddy Waka, leading a part of the storage software team at Fungible. I'm with Fungible almost from 6 years, almost since the inception of our idea of DPUs. So today I will be talking about data processing units. One of the important use cases of the data processing units, DPU as a storage initiator, and how it is enabling the high performance storage disaggregation. So as well as the bare metal virtualization, right? So we started with this idea of developing the DPU for data centers. It's purpose built, and today I'm going to take you through one of the important use cases, which is the storage initiator. So in the agenda, first I will talk about why do we need DPU in compute nodes. There are many reasons. Most of my talk is focused on the storage initiator part of storage initiator use case of the DPU. And then I will talk about DPU as a storage initiator. What are the things that DPU can do for storage initiation? I will talk about the value add, the benefits, as well as I'll deep dive into our architecture, software architecture, and why our architecture is unique and how it can provide the best performance. And then I'll talk a bit about the integration with the orchestration systems, showing the whole ecosystem around it, and how the SI can be integrated seamlessly into the existing orchestration systems. And then I will conclude with SI performance, some of the performance results that I can share today. I'll conclude with that. And feel free to stop me if you have any questions. I would love the two-way conversation as much as possible. So why DPU in compute nodes? So I see many reasons, and one of the first and important reasons is we need to pool the resources. So as the data centers have evolved, and people have realized that the data center is like one big giant computer. It is not CPU centric anymore, and there is a transformation of CPU centric to the data centric model, right? Data centric based designs of the DPU of the data centers. So we need to resource the pool. We need to pool the resources for efficiency and reduce TCO. So what does it mean? We need to take out all the resources that are with the individual servers, individual application servers, and pool them such that they can be shared by all these servers, so you get the benefit in terms of the cost, right? So the storage, memory, GPU, any resource that was CPU centric before can be made data centric by going through a DPU. And then there are demands. Always the demands are increasing from the infrastructure as well as the modern applications like AI, ML, analytics. So all those applications are putting stress on the application server CPU, and server CPU is not able to scale as it used to be, right? So the storage speeds with SSDs, today we are over 1 million IOPS, a single SSD, and they're going towards 2-3 million IOPS. And the networking speeds like 100 Gbps, 200 Gbps, and even 400 Gbps is on the horizon. And security, we are going towards the zero trust security model in the data centers, which means you need a lot of security in the hardware. So all these demands together with the application demands are putting the stress on the server CPU, and server CPU is thinking, what do I need to do? How do I scale, right? So the immediate obvious answer is I need to offload the work that I am doing, that I shouldn't be doing, which is servicing the infrastructure, right? And then the bare metal virtualization. Again, the main drivers, the way I think it is it's the security and performance. These are the two main drivers for running the bare metal virtualization. So we don't want any overhead of the virtualization software between the VMs and the bare metal. So this is another driving need, and this is where so you need to run the infrastructure as well as the hypervisor that's virtualizing the CPU as well as the memory in the hardware. So DPU is a perfect place where you can run it. So all these reasons are driving the need for DPU in the compute nodes. So I'll start with an overview of the fungible client DPU, which we call it as S1 DPU. And as I said before, the DPUs are purpose-built for data-centric processing. And this is the client DPU that is targeted for the compute platforms, where the DPU can offload storage, networking, and security, right? So we have 200 Gbps networking, the PCIe Gen 3, Gen 4 with 32 lanes, the SRIO we support for the IO virtualization. So we support up to 32 physical functions and 512 virtual functions. And built-in accelerators, a lot of hardware accelerators that support the storage and networking offloads. And we have 16 MIPS 64 cores running at 1.6 gigahertz, providing the compute power that is needed. And the data sheet is on our website. You can read a lot more about this DPU. So at a high level, you have a big networking pipe, as well as your PCIe pipe towards the host, right? And then you have a lot of computing, where like we have hardware and software are working together to provide the best performance. So I'd like to show you the Storage Initiator use case. We can offload the protocols, all the NVMe over Fabrics protocols, the latest state of the art like NVMe over TCP, including the security if you want to offload the TLS, as well as Rocky. And then we have our own technology called True Fabric. So all these protocols can be offloaded. So this is significantly saving cycles, the host CPU cycles, as well as a lot of data processing tasks, like for example, the CRC, which is required for data integrity, as well as encryption, compression, erasure coding, all these, we have accelerators in the DPU. So we can take advantage of those, and we can offload all these tasks from the CPU to the DPU. So as you can see in the first picture, you have applications doing this CRC, encryption, compression. They're all taking the CPU cycles. And then you have the drivers, the NVMe driver, NVMe OF in this case, and it is talking to a TCP driver, and it's talking to a NIC driver, and then it is talking to the smart, right? So now you replace that with the DPU. All you need is the NVMe driver between the app and the DPU, right? So the app is directly talking to the NVMe driver, and then the NVMe driver is talking to the DPU. DPU is taking the storage IOs from the application and then sending them over the network to the remote storage. So what are the biggest value add, right? So one is we provide high performance storage disaggregation, right? So the remote storage, as shown in the previous picture, right? It looks like local storage. So there is so the host CPU looks like, okay, I have a device on my PCI bus. It looks like a local storage. I can just use it. And this means, as shown in the previous picture, a lot of the work that it used to do before, it doesn't have to do to process the IOs. And we have a very unique architecture in the sense that the MIPS cores, the processing cores, or you can call them as virtual processors, VPs, and the hardware blocks, right? They are tightly integrated, and they're tightly integrated in the way that we can pipeline efficiently. What it means is today, if you want to, you can do this on the host CPU. Today, if you want to do the pipelining on the host CPU, and if you want to go from one processing thread to another processing thread, there is a overhead, right? So how do you minimize this overhead? This is one of the innovations that we have in our DPU to minimize the overhead in dispatching the work. So at the end of the day, you need async programming. What it means is you never want to stall. So to avoid the stalls, you do want to dispatch the work. You do whatever work you can do, and then you want to dispatch it to the next guy. So basically, our architecture allows an efficient pipelining of the flows. And the hardware accelerators are inline, and they provide a lot of the benefit in terms of the performance. Right? And then we have the SRIOV with multiple PFs and VFs. They enable the bare metal performance to the VMs. So whatever performance the bare metal sees, the virtualized environments will see the same performance, right? And then you can offload storage processing. The storage and network protocols that the NVMe or Fabric or any other storage and network protocol can be offloaded. And today we support NVMe or TCP. And the storage service offloads like encryption, compression, CRC, and security can be offloaded to the DPU. And the DPU enables the bare metal virtualization by emulating the devices, by allowing the IO virtualization and the composability of this storage and networking without depending on the server OS. It means like we need to separate the infrastructure from the server's OS. And that's exactly what we are trying to achieve by doing that in the DPU and making the DPU as a key enabler for the bare metal virtualization. Right? And since we are emulating, we can emulate a large number of storage devices. And it's really like, limited to like your resources, like, the memory that you have within the DPU, things like that. It's mostly a software limit that you will run into before you run into any other limit. And then the security, least but not last, right? So this is one of the important drivers for the DPU, right? The storage security, which is very important and you need the encryption for data at rest as well as the data in flight. So we do support encryption inline, and we also support like TLS v1.3 and in-band authentication, right? With very little impact on performance because of the inline accelerations we have. And then you need hardware enforcement of storage security policies, which may require deep packet inspection, and all of this can be done within the DPU. Please.
If NVMe traffic is going through the DPU, how much does it add to the latency?
Yeah. So the question is like, how much DPU is adding to the latency for the IOs, right? So if you're comparing the latency that you see at the host without the DPU and with the DPU, there is a benefit that the DPU is bringing, because a lot of the processing that the host is doing, it is not doing anymore. So you're saving latency there. But the processing within the DPU, we expect it to be less than 5 microseconds. The whole processing, because of the pipelining that we have, and the pipelining as well as the hardware accelerators, the total latency that we see, including the encryption and compression and the CRC calculation. So we do the CRC as the data is moving from the host memory into the DPU. So it is in line with no additional impact on latency for the CRC calculation. Thank you. So other benefits, multi-tenancy, which is a very important factor with QoS. So the moment you have multiple tenants, you need to be able to provide QoS, adhere to the SLAs that are required. So which is easy to support in the DPU. Once you have a lot of these volumes that you're abstracting, which we call as remote volumes. So the actual storage is on the back end, right? The initiator is like a proxy. It is so you can have the SLAs for all these volumes, different SLAs for the different volumes, right? So and it is highly programmable. So we have our SDK, and you can quickly roll out any new features. And high availability, which is one of the important considerations for any storage. So the DPU handles the multipathing and failover. So what it means is we use the NVMe or TCP, and we follow the standard, the ANA, asynchronous namespace access. So the storage composer, that is a piece of software that's running on few VMs or few servers, and that is our way of composing the infrastructure, right? So that is our piece for composability of the infrastructure. What it means is it allows you to create the volumes, it allows you to create the volumes in the target cluster, and have the remote volumes created in the initiator, and then have them connected over the NVMe or TCP. right? So when you do this, you can provide the multiple paths to the initiator. So usually 2 paths, right? So you give your primary path as well as the secondary path. So the initiator, the DPU acting as the initiator, it is connected to the targets, 2 targets, one over the primary path and another over the secondary path. If primary path goes down, and the ANA comes into picture because the target can advertise whether it is an optimized path or an inaccessible path. In other words, active path or inactive path, right? So you are connected to 2 targets for a given volume, and one of them can be active or both of them can be active, but the initiator has to decide based on its policy on how to choose the paths. So all of that is completely handled within the DPU software. And we support end-to-end data integrity. So a lot of the applications, they do need this feature, and this is one of the important features. But the diff is like, not many people implement, right? Not many applications actually implement. But we can provide the end-to-end data integrity now from the initiator DPU to the target DPU, and we already added the support for that. And we take advantage of the hardware CRC accelerators, so we don't incur any performance hit. And then the ecosystem that I mentioned initially, like, we are using the standards-based NVMe standards-based protocols, and the NVMe TCP, NVMe over RDMA, Rocky, as well as we use the standard NVMe discovery. So the discovery service is running in the storage composer, so that the initiators can find the targets by talking to the discovery service. Yes.
Storage composer runs CDC?
Yes. Centralized discovery code. So the question is, does the storage composer run the CDC? Yes, the answer is yes. Yes, we have a CDC running inside the storage composer. And then our composer, it provides the REST-based intent API. And so it provides the REST-based intent API, and the API is a very simple API in a way, like, we can easily integrate with the orchestration systems, right? And we have integrated with the Kubernetes and OpenStack. And low power, so because of the small footprint, the power that you spend per IO goes down, as well as your cooling requirements. And then this enables the diskless servers, because now you don't need the local disks anymore. You can completely rely on the remote disks. So we support the remote boot of the bare metal as well as the VMs. And because we are compressing the data at the initiator, you are reducing the network traffic. And there are other things like, you can cache on the client side, so the DPU can support that cache, as well as you can do the direct reads. So in case of durable volumes, you usually, like, you go to a master node and then it goes to some other node and then gets the data. But that can be avoided by talking to the client and directly giving that information. Oh, here is your data for your reads. For writes, you most likely have to go through a master node, but for reads, you can do a direct read. So now I'll deep dive a bit into the architecture that we have. So this is where, like, we have some unique capabilities. As I walk you through, you'll understand a bit on what I meant by those capabilities. So the software is very modular. The first reason for this modularity is, of course, like, it's so one thing is, like, is the development. Right, you do want to make sure that the development can go in parallel, but more than that, here it is the composability. So what it means is you have a lot of NVMe endpoints that need to be emulated, right? And then you need to establish a lot of the TCP connections or the Rocky connections, right? So, and then you have the volumes in the middle. So you need to compose all of this as needed. And that's where, like, the modularity helps a bit, right? Helps a lot. So the data, the NVMe driver. So this is PCIe. So this is the PCIe interface, NVMe or PCIe. So the IO start from the application server, right? The NVMe driver puts it in the one of these submission queues, and then rings the doorbell, and then our PCIe unit, right? It starts fetching the data using the DMA. So we process the descriptors that are in the ring in this NVMe emulation logic, right? So basically, fetch every request, go and figure out go and fetch the data from the host memory. If it is a write, or if it is a read, you write back into the host memory. So that's handled by the NVMe emulation, and each function needs an NVMe controller. Each PCIe function, since you support a large number of PCIe functions, each of them is a PCIe controller, and for each PCIe controller, you need an NVMe controller. That's a one-to-one relationship. And that is, and again, that can be configured to be a different subsystem, and every subsystem is identified by an NQN, right? NQN is uniquely identified by an NQN. In this case, it is host NQN. So we provide that information, and we create those NVMe controllers, right? And then we can have the data go through these accelerators, the CRC, compression, encryption, and then it goes to a remote volume, which is an abstraction of the volume on the target cluster, right? And then it goes through the multipathing and failover logic, and then through the TCP or the ROCK, whatever the transport that you use. So the first important point in software architecture is we are run to completion model. It is async and run to completion model. So each processing thread or VP is basically, it is in a tight loop. The operating system is very simple, that every processing thread is in a very tight loop, taking the work that is the incoming work, doing the work and dispatching some work out, or completing the work, right? So there are no stalls there. And then the dispatch, usually you can call it as context switching overhead if you're in the CPU world, right? The time it takes for you to dispatch is very minimal. We are talking of the order of 30 to 40 cycles. So we minimize the context switching overhead, and there are no interrupts. Everything is what we call as work units. Basically, they are messages going between the processors. And then the pipelining, as I said, a given volume is pipelined through these several stages. As you can see here, there are 5 stages in the pipeline, or it could be the multipathing logic could be more than one stage. So we have pipelined into multiple stages so that a single flow can achieve the maximum performance. You don't need multiple volumes. Even a single volume can achieve the maximum performance that you can get, right? And not only, and another important point is you have many of these processing threads, and you need to place all the volumes on these processing threads, all the volume flows, right? Each flow is a chain of 5 or 6 stages, and you need to place all of these on these processing threads according to the SLA requirements. So you need to make sure that the resources are allocated in a way that each volume can meet its SLA, right? So this placement, all of this is taken care as we create these volumes, right? As the composer is sending the commands to create the volumes, we handle all of the placement of the volume flows. And there are many of these pipelines. They're all so a given processor is running parts of the many pipelines, right? And then efficient data movement. So we never touch the data in the software that we are running in the DPU. The data moves through the engines, through the hardware engines, right? So it is DMA. It is from the host memory, it gets DMA'd into the DPU memory, which is on-chip memory, and then it's DMA'd through the accelerators, and then onto the wire, right? And we have a huge bandwidth for the DMA, so it's not a problem at all. I'm talking about terabits, 1 to 2 terabits per second. And then the inline hardware accelerators I mentioned a couple of times already. So one thing that I do want to mention here is that we have multiple threads. So you have a compression engine, you have multiple threads of this compression engine. So we have several pipelines, so all of them can simultaneously use these engines, and there is a load balancing that happens across the engines. And that's again for efficiency, right? The composable data plane. So the data plane is fully composable. by an orchestration system through the storage composer. And basically the operations that you do is the normal operations, creating, deleting the volumes, attaching, detaching them to the controllers. So you create the volumes, you create the controllers, and you attach these volumes to those controllers. The NVMe controllers, which correspond to some PCIe functions. Right. So we abstracted the controllers, the volumes, device. These are the right abstractions for the composability that we looked into. And then the per volume composability. So each volume is independently composable. Each volume has its own property. Some volumes may have encryption, some volumes may not have encryption, right? Some volumes may enable CRC, some volumes may not enable CRC. All these volume properties are composable, and it is composable at the granularity of per volume. And the last bullet is is a very important aspect of our software architecture, log-free. We don't rely on the logs. The way we achieve this is because we are run-to completion model. As well as we associate these flows with the processing threads. So any pipeline for a given volume has certain stages, and they always run on the same set of VPs. Same set of processing threads. So you never need, and the state is maintained on the same VP, and it is a run to completion. Nobody can interrupt you. So there is no need for the log at all. Right? And cache friendly, right? Every time you have a cache miss, you have like 200 cycles lost, right? 200 to 250, depending on whether it's L1, L2, right? Where the miss is at. So as the processing threads are trying to pick the work, there is a prefetch that is happening in parallel. So there is a work that is sitting at your input queue, and as you're about to finish the work that you're currently handling, and before you start picking the next one, we also start the prefetching, and we try to maintain the data structure such that they fit into the cache lanes, which is the usual case, right? So that's pretty much about the architecture that we have and why we are able to achieve the high performance. Now I'll talk a bit about the integration, how we integrated with the OpenStack. So as many of you know, OpenStack is a cloud operating system for orchestration, and it allows orchestrating all the infrastructure like storage, networking, security, and other resources. And Cinder is one of the services in the OpenStack, and that is responsible for managing the block storage. And it allows the vendor plugins. So all we need to do for integration with the OpenStack is you develop a Cinder plugin for your storage and submit it to the upstream open source. Right? So it provides, the Cinder provides, it virtualizes pools of block storage devices, and it provides users with consistent API to access different types of storage. So these Cinder drivers, they can communicate with both the targets and initiators. So as you can see in this case, so we have a fungible Cinder driver that allows all those functions, creating, deleting the volumes, attaching, detaching, expanding, creating the clones, creating the snapshots, right? So the intent API, the Cinder driver it's a plugin, and it supports the Cinder API. So any requests that are coming from the Cinder driver takes and gives them to the storage composer, which goes and talks to all the SI devices as well as the target cluster, the storage cluster, right? And the Nova is another service responsible for compute, launching the VMs and then associating the storage with the VMs, right? So for this association, this is what you call attaching, detaching. So it needs information like which volume is attached to a particular VM. So that is achieved by passing the information between the Cinder and the Nova. And the volumes are identified through the unique identifier NGUID. So here the data path is shown in the red, and as you can see, it's directly going from the storage initiator to the target, right? And the control path is shown in the green there. So this picture is very similar to how we have integrated with the OpenStack. So this is how we integrated with the Kubernetes. Again, it allows the CSI plugin. CSI stands for Container Storage Interface. So it is a specification for developing the plugin for the container orchestration systems. So it has defined GRPCs that the container orchestration systems can invoke for provisioning and attachment, right? And one plugin works across multiple COs. We have tested with the Kubernetes. So other COs like Cloud Foundry and Mesos can use the same plugin, right? So these plugins allow attaching, detaching the NVMe namespaces to the containers. They allow creating, deleting the volumes, and defining new storage classes. So that's one of the important features of the CSI plugin. You can define new storage classes. What does it mean is, like, you have different types of volumes with different properties. So you can define all of them as new storage classes, and then you can decide which storage class you want to create and then associate with which VMs, which container. So the composer creates an NVMe namespace in the storage initiator and connects it to the storage target via multiple paths and attaches it to the right PCIe function. And then the kubelet associates the NVMe namespace with the container by finding the info from the storage composer via the CSI plugin. So the CSI plugin runs in both the worker node. There's one of the nodes acts as a master node, any one of the worker nodes. So the plugin runs in all the worker nodes. Right. So now I'll move on to the benchmarking setup that we have. So it's a very simple setup where you have one application server with a smart NIC and another application server with a Fungible S1 DPU platform, right? And then we have the Fungible storage cluster as the storage target. And all of these are connected via a TOR 100 gig switch. And then we also have a packet sniffer for debugging and other purposes. And then there is a storage composer that runs in a few servers for the high availability. And that is also connected to this, all the DPUs. So the DPUs on the initiator as well as the DPUs on the target. So now we can go to the UI. We have a UI to use the composer. So we can go to the UI and create the volumes and attach to the VMs and start running the workloads, the FIO or any other workload. Right. So these are the results that we see today. With the Fungible FC200, which is using our client DPU, S1 DPU, we are achieving more than 2.5 million IOPS, random read or write IOPS, right? And it delivers the same performance to the bare metal as well as the VMs through the VF pass-through. Right? So what is the benefit it is providing? Right? So if you compare the host CPU utilization, this is the comparison from all the starting with 700K IOPS all the way to the 2.5 million IOPS. So we measured more than 10 CPU cores saved per 2.5 million IOPS. So each S1 card, each FC200 card that you plug in and use it as a storage initiator, you're saving at least 10 CPU cores. So today, most of the servers use 30 to 40% of the CPU power just for infrastructure processing, and that can go down to 15 to 20 cores or even lesser.
In both of them, you are using basically kernel initiator, right?
So the red line, let me go back. So we have one server with smart NIC, right? So that's the red line. So there it is using the kernel initiator. In the other case, it is NVMe. So there is it's NVMe driver. There is no NVMe over fabrics. So the NVMe over fabrics is handled within the DPU. Within the DPU.
My question is that do you have any comparison with user space initiator?
User space initiator, SPDK. Yeah. So we have done. I'm not sharing the numbers here, but the SPDK publishes numbers regularly, and they compare with the kernel initiator, right? So we are significantly better even when compared with the SPDK initiator. I don't have any specific numbers to share here, but we have done that comparison.
If we use SPDK initiator, then none of the fungible DPU features will be used.
Today, because it is handling everything in the user space, and it is still using, I believe it's still using the kernel's TCP stack,
Yeah.
right? So it's handling the NVMe over fabrics in the user space. Yeah, but you still have a significant savings because when you use the DPU, you are not running the TCP anymore on the host CPU. So another thing that I wanted to mention is like, when you have the VMs running, the typical VMs, they see at least like, twice please go ahead.
Question here. The comparison point is the smart NIC, but you mentioned it's not offloading the TCP stack. So isn't it just a NIC?
Yeah, it's used as an L2 NIC, yes.
So it's just a plain NIC, right?
Yeah, most of the operating systems today, they don't support the TCP offload natively, but you could try. You could use the TCP offloaded, yes. Yeah, that will give you some benefit as well, yes.
But
In this case, the TCP is run. In one case where you're using the smart NIC, the TCP is running on the host CPU. Yes.
in this chart, it's okay, I don't request something like that.
Yes. So all of these are 4K random reads and no gimmicks in like conversion of 512 byte requests into 4K or 4K. No caching, nothing. Please go ahead. Right. So yes, for 100 Gbps, so at 4K, correct. So yes, obviously you have a limitation in terms of the compute power that you have inside the DPU, right? So we can optimize and we can go to the 2.8. We are very close, as you can see in these numbers. 2.6 and 2.5. But the higher the IO size, you would saturate the bandwidth anyway. So this is the block size is 4K, the IO size is 4K. The moment you go to the 8K, then the IOPS that you need to saturate the 100 Gbps or 200 Gbps is much lesser, right? It's half. Yes.
So I assume there's no other traffic on your network and no congestion, not at all.
So here the DPU is totally used as a storage initiator, but we do allow a partitioning between the storage and networking. So you can use a part of that. So the same DPU can do the networking offloads as well. You can use it as a networking device as well as a storage initiator, right?
How sensitive is that to TCP congestion then?
So yeah, yes, that's a very good point. The TCP congestion is a major factor in any of the TCP-based designs, right? So we implemented TCP inside the DPU, and we handle the congestion in the DPU. And we have implemented almost all the standard congestion algorithms, and it's no different from how the TCP runs on any host stack. But yes, yeah, that is where the other transport protocols like Rocky will benefit, right? And as well as we have a technology called True Fabric, which I kind of mentioned earlier. We do that's especially targeted to solve this problem, right? The avoiding the congestion. It's not even reacting to the congestion; it is trying to avoid the congestion. Yeah.
You just mentioned that you can actually use the DPU ports simultaneously as just plain NICs, so they will show up as each device?
Yes, we have multiple physical functions, PCI physical functions. So some of the functions we expose as the Ethernet devices, just as plain NIC, and some of the functions show up as NVMe devices.
Which, if it's actually connected to a target, will show up as like dev.
Correct.
NVMe.
Just like if you do ls/dev/NVMe, yes, yeah, you will see all those devices. Yes, please.
What kind of scale testing you've done in terms of number of connections and number of volumes?
Yeah, very good question. So Initially, when we started, we were like with 256 volumes or so, but today we support up to 1K volumes. But again, the number of volumes is really a software limitation, right? How much data you need, how much you need to maintain, the state you need to maintain per volume, right? So how much on-chip memory you have. That's really the limitation. In terms of the connections also, again, it is limited by the memory, but each of the volumes has like, 8 to 16 connections going towards the target. So you can multiply the number of volumes with the number of connections. And last year November, like one of our customers, they have used like 4 or 5 of these cards in one server, and they were able to achieve more than 10 million IOPS. Right? It simply scales as you add more cards. Right? Which is the case with so if you don't have those cards, it's almost impossible to get to the 10 million mark. Yes, please.
What's the extra latency introduced by putting the storage or the flash remotely instead of directly into the server?
Can you say the last part again? Instead of direct.
What is the extra latency introduced by having the flash on the remote end of the network versus having it directly installed within the server?
Oh, okay. So yes, you obviously have the network latency, right? So you are adding the network latency as well as the processing latency within the DPU. So the processing latency within the DPU is under 5 microseconds. So it's really like, it's really very, very competitive in terms of, and you're saving latency in terms of the host processing. So it comes down to a latency benefit of using the DPU. You actually see a benefit in terms of the latency. I don't have the numbers here, but we did measure, and the average latency is actually less compared to the software initiator where the TCP and NVMe over fabrics is running in the host. Yes, please.
So the card is a PCI Gen 4 by 16 lanes?
So it has 32 lanes, but you can, today like most servers, you have a by 16 connector. So you have 200 Gbps network, so by 16 Gen 4 is good enough for you. But the other 16 lanes can be used for local storage, for use cases like local instance storage, which I didn't talk about here. But yeah, you can connect them to the local storage devices and use that.
What's the power consumption?
I don't have that number.
The card? Yeah. What, 35 watts?
Thanks, Jay. Okay, so on the what type of performance, so this chart is showing like, the percentage of the read IOPS or the write IOPS that the VM is seeing compared to the bare metal, right? So if you don't have the DPU versus you have the DPU, so it is clearly showing the benefit of 2x. This is a typical VM.
That should just say NIC, it shouldn't say smart NIC, I think.
Yeah.
People get confused.
Yeah, so it's just an L2 NIC. Yeah, smart NIC. When I meant smart NIC, it doesn't have any TCP offload. Just to clarify, so you're comparing like a software initiator which is using the L2 NIC versus a DPU-based storage initiator.
But there are some vendors who have DPUs, right? Have you tested like apples to apples?
Yeah, I haven't. I haven't seen like any numbers coming from them, and we don't have access to those devices yet. But we will be doing that.
There's some comparison.
Yes. Absolute. So this is actually a number coming from our customers, and we also verified that. And this depends on like how the VM is configured. What I wanted to show is a typical VM with 4 to 6 cores. You would see like double the performance that you would see otherwise. So as you have more cores in the VM, you would see almost like up to 2.5 million with less number of cores. Pardon? Right, the more the cores that you can give, right, it is limited by the number of cores that the VM has. Correct. So the bare metal can see the full performance. And the same performance can be seen by the VMs. You can have multiple VMs, right? and the multiple VMs are a single VM with multiple cores, many cores, can see similar performance. Yeah, I don't have those numbers right now, but okay. So there are a couple of other presentations from Fungible. So on Monday, Jaspal presented next generation architecture for scale-out block storage. You can refer to that if you're interested. The talk is mostly about the architecture for the scale-out and disaggregated block storage. Right? And the talk that is coming up next, it's really comparing DPU-based storage with the CPU-based storage and the benefits. It's really an exciting talk, and it's talking about why DPU is going to be the ASIC for the storage systems. Right? And finally, I would like to acknowledge the entire Fungible team who made the DPUs a reality. This was the vision that our founders had 7 years back. And today we have the DPUs used as storage targets as well as the storage initiators and other applications like SDN appliance and other things they're possible as well. And thanks a lot for listening. If you have any questions, please go ahead. No open source. It's completely developed because as I said initially, we have a very unique operating system, and we have a very highly efficient messaging that's only possible through the hardware changes that we were able to make to the MIPS cores. So yeah, that is another option some vendors are pursuing, but we believe we can get the highest performance with our architecture. Yes.
I'm curious, what is the presentation model for the NVMe namespaces that you virtualize and present as NVMe devices? So let's say if I have multiple namespaces provisioned to a bare metal.
Mm-hmm.
Correct.
So if you have correct. So if you have attached them to the bare metal PCIe function, right? They will show up on the. So if you're talking about the host operating system, right? But if you're using VF pass-through, they will show up to the VMs directly. They don't show up in the hypervisor, right? So if they're showing up in the hypervisor, you could use them with containers, or you could use the virtIO, right? That's virtIO block. Yes. So for a given, so that's the NVMe spec. If for a given PCIe function, it is one controller, right? So they will all show up as NVMe 0, 0N1, 0, N2, 0, N3. That's the naming model, right? So under a single, correct. Single subsystem, single controller, multiple namespaces for each PCIe function. So as I said, today we are really it's the number of volumes that you can support. It's the memory that is limiting. So we are supporting up to 1,000 volumes on a given DPU. So each volume shows up as a namespace. Yes.
So is it necessary to have that composer in the network, or it can be?
So yeah, as you rightly mentioned, there is a CDC running inside the composer, right? From the initiator point of view, it is really which targets I need to connect to. So we could easily integrate with any other CDC. Yeah, so we have run experiments, we have run the tests with the SPDK target, with the Linux target, not just our own target, right?
And the multipathing that you have, is it active failover kind of a thing, or it's round robin, least queue length, what kind of a?
So it's active passive model. It's not active. One path is active at any time, and it is very important that your writes always go to one node, and you don't have a split brain situation. So we handle that.
But if the storage target has multiple paths to the same active controller, and everything comes back as active optimized, so you still choose
Right. So the initiator design it's policy driven. So if you have multiple active, you can do round robin. That's one of the things that we do. But you can have any other policy if you have more than two, right? You can choose any other policy. But if you have only one active path, you don't have a choice. But one thing that we do is we hold the IOs for a certain time before we time out to the host. If one of the paths goes down, we wait for the other path to come back up.
And each of your pipeline stage, is it a different core or it's like a?
Yes, it's a different core. Each stage runs on a different core and on the same core.
And like how many, like you have DMA engines per core? Like how do you
Yeah, so all the accelerators, like we have DMA engines, the encryption, the compression, all these accelerators do the DMA, and they are there in every cluster. So we have a couple of clusters, and each cluster has 8 cores. So we have total 16 cores, 2 clusters, and there are a given number of accelerators in each cluster, and each accelerator is multiple threads, so they can be simultaneously accessed.
How many PFs you have per
32.
So all these numbers were collected with one PF multiple namespaces or?
So we have done both ways.
And
So
one PF you can maximize the whole.
yes. Yeah, you have a Gen 4 by 16. And yeah, all you need is one function. Okay, thank you very much. Thanks a lot for listening.